So I've been a medical illustrator for about 35 years. And for about 30 of those 35 years, I've done a lot of molecular illustration work. It all started because I had a client who was an oncologist, a cancer doctor. And he published a series of continuing medical education materials. And he wanted lots and lots of pictures of chemotherapy drugs, the actual molecules that responsible for chemotherapy, as well as the proteins and other molecules in the body that the chemotherapy drugs interact with. So I found myself needing to find good references for how to illustrate these kinds of molecules, both the drug molecules, which we would refer to as small molecules, and then some of the larger things like proteins and nucleic acids and so forth. And during that period of time, it seems as though the need for illustrating things at the molecular level has continued to increase to the point where now I feel like just about anybody in this profession is very likely to end up illustrating something molecular at some point in their career. If you work for a teaching hospital or medical university, pretty much guaranteed you're going to be doing some molecular work, because that's where most of the cutting edge research in medicine is right now. Developing medicines, understanding the molecular basis of diseases, infections, vaccines, things like that. If you work in publishing, particularly journal publishing, there's a very good chance you'll end up doing a lot of molecular work. Like we have several people on staff at Science Magazine. We have several people on staff at the New England Journal of Medicine. They do tons of molecular stuff because these are two of the top science and medical journals in the country, and they're publishing all of the cutting edge research, much of which is molecular in nature. One of the few areas where you probably wouldn't do very much molecular work would be medical legal, because it deals primarily with anatomy and surgery and injuries and things like that. But even there, I know there are occasional cases that involve things like administering the wrong medication to a patient. And what's happening at the molecular level, what kind of interaction occurs when you give people two medicines that shouldn't be mixed, or if you give them too much of a certain medication, what's happening on the molecular level. So even in that area, there are times when you may find a need to be able to illustrate things at the molecular level. The other thing that I've found over those 30 years, give or take, is that knowing some chemistry has been incredibly helpful to me as I try to understand molecular structure and to ensure that what I'm illustrating is accurate. So knowing some basic chemistry, like the structure of the atom, the way atoms bond to one another, the geometry of the bonding, the angles that are formed between different kinds of atoms when they make multiple bonds, but also understanding things like the structure of the major classes of biological molecules, proteins, nucleic acids, carbohydrates, and lipids. So for the rest of the semester, we're going to be dealing with things at the molecular level. So I'm going to start out today with an introduction to just basic chemistry, which I hope is largely review for all of you. I could go into so much more detail. Those of you who've had a fair amount of chemistry are going to be very thankful that I don't get into like hybridization of orbitals or any of that stuff. So there's not going to be any DSP3 on orbitals or any of that stuff, which is the bane of many students' existence, trying to learn that stuff. I'm going to use a very simplified model of the atom, which is perfectly adequate for what we need it for. And then later in the course, I'm going to introduce specialized molecular visualization software. Like we looked briefly at Chimera X the other day, which is one of the tools that we use for actually viewing molecular models. I'll talk to you about where to find these molecular model files on the internet, how to find these 3D models online. There are a whole bunch of databases of molecular models that you can access online for free. And I'll also come back and give lectures about the major classes of biological molecules. So there's a whole lecture just on proteins, a whole lecture just on nucleic acids, and another one on carbohydrates and lipids, because they're a little bit simpler. So let's go ahead and get started by reviewing the structure of the atom and then talking about bonding and the concept of valence, and then geometry, the angles that are formed between bonds. So you're probably all aware that all matter is made up of atoms. This notion goes back to the early 1800s. And since then, it's been very well proven, very well documented that all matter is in fact made up of atoms. Atoms, in turn, are made up of smaller particles known as subatomic particles. And this includes the proton, which has a single positive charge, a charge of +1. And all of the protons are located in the nucleus. There are also some particles that have no charge, that are electrically neutral. These are called neutrons. They're also located in the nucleus. And then there are the electrons, which have a negative charge, a single negative charge, so a charge of -1. And these things are orbiting around the nucleus, kind of like the way the planets orbit around the sun. So you have electrons orbiting around this much larger thing in the center, which is the nucleus made of protons and neutrons. The fact that the protons have a positive charge and the electrons that are whizzing around them have a negative charge, that's what actually holds the electrons in their orbits and prevents them from simply flying off into space. Similar to the way the gravity of the sun is what prevents our planets from just flying off into the universe. So the attraction between the sun and the planets is what holds them in their orbits. And so similarly, the attraction between the positively charged protons in the nucleus and negatively charged electrons orbiting around it, that's what holds them in their orbits. There are a couple of numbers that are going to be very important things for you to be familiar with. These are numbers that describe specific atoms and tell us a little bit about the chemical behavior of these atoms. The most important number, especially for our purposes, is what's called the atomic number. The atomic number is simply a count of how many protons are located in the nucleus of the atom. And that is really, really important because that determines exactly what kind of element it is. The number of protons in the nucleus is what distinguishes hydrogen from helium, from carbon, from oxygen, from uranium. Every single element has a specific number of protons in the nucleus, and that's what defines what it is. For example, hydrogen has a single proton in the nucleus. That's what makes it hydrogen. Helium has 2 protons in the nucleus. That's what makes it helium. Lithium has 3 protons in the nucleus. That's what makes it lithium. So that number of protons in the nucleus determines the identity of the atom, what kind of element it is, and determines most of its chemical behavior. In particular, what kinds of bonds it forms. So that's going to be a very important thing for the rest of our discussion today. Now, it is possible to change the number of protons in the nucleus of an atom, but when you do that, you're actually changing what kind of element it is. Right? If you somehow manage to take a large atom and split the nucleus into smaller pieces, you end up with 2 completely different elements. This is actually what happens in the process of nuclear fission, which is the process that takes place in nuclear reactors. And it's the thing that powered the atom bombs that were dropped on Hiroshima and Nagasaki at the end of World War II. So you can probably tell that this splitting of the nucleus, this process of atomic fission or nuclear fission, releases a lot of energy. So you take usually a large nucleus with something like uranium or plutonium, which is highly radioactive, very, very large nucleus, and you split that nucleus into smaller pieces and release a lot of energy. So that's nuclear fission. You can also do the opposite. You can take smaller atoms, things that have rather small nuclei, like hydrogen, and you can smash them together in such a way that their nuclei actually combine. And once again, you create new elements. If you take two hydrogen atoms, each of which has a single proton in the nucleus, and you smash them together so that those protons fuse to create a new nucleus with two protons, you've made helium. So you've literally changed one element into another. That's a process known as nuclear fusion. And that's what powers the sun. The sun is a giant ball of hydrogen, which is continually undergoing the process of fusion, where those hydrogen atoms are being combined to make heavier things like helium and possibly other elements. It's also what powers what are called hydrogen bombs, which are very different from atomic bombs. The bombs that were dropped on Hiroshima and Nagasaki, as horrible as they were pretty weak compared to an H bomb. Hydrogen bomb that uses fusion as a source of energy is like 1,000 times more powerful than an atomic bomb. And there's actually been some stories in the news lately about a couple of different countries. I know there's a research group in China, another research group in France that are trying to harness the power of nuclear fusion as a source of essentially unlimited energy. The problem is you have to contain it, because if it goes nuts, you blow up a whole city, which is not a good thing. Yeah. So these two processes of fission or fusion, we're not going to worry about them at all the rest of the lecture or the rest of this course, because that's not something we normally have to illustrate. But I just want you to be aware that there are these rare situations where you literally change the number of protons in the nucleus, but then you are literally changing exactly what kind of element it is. We're going to stick with things that have a consistent atomic number. So here's the really simplified model of the atom. Again, looking a little bit like our solar system. We've got the nucleus in the center, and the little white circles are the protons with the single positive charge. Little gray circles are the neutrons with no charge. They have a neutral charge. And these make up the nucleus of the atom. This is also what gives the atom most of its weight. The electrons are trivial. They have almost no mass, almost no weight to them. And then you've got these electrons that are kind of whizzing around. And there are many ways in which this is simplified. I mean, they don't follow these nice uniform elliptical orbits. That's one big difference between an atom and our solar system. The planets whiz around the sun in a pretty much predictable elliptical orbit. Electrons are just kind of buzzing around like a bunch of bees buzzing around a hive. And there's a whole field of quantum mechanics which tries to understand the statistics. What's the likelihood that an atom is going to be, or an electron is going to be in any one location at any given time? Thankfully, we don't have to get into any of that stuff in this class. So there's this other number that's often used when we're talking about atoms. This is the atomic mass, or sometimes simply just the mass number. And this is counting not just the protons in the nucleus. Remember, the atomic number is just the number of protons in the nucleus, which determines most of the atom's chemical behavior. The atomic mass, or mass number, is counting both the number of protons and the number of neutrons, because it's those two particles that give the atom most of its mass or most of its weight. Remember that the number of protons, that atomic number, is always going to be constant for any given element. So helium will always have 2 protons in the nucleus. Carbon is always going to have 6 protons in the nucleus, and so on. If it didn't have that many protons, it wouldn't be carbon anymore. The neutrons, on the other hand, can vary without changing what kind of element it is. And we'll talk more about that in just a few minutes. When you look at the symbol for any given element, like the symbols that you often see on the periodic table, there are frequently a number of numbers scattered around the symbol itself. So here we have an example of the periodic table symbol for helium. We have the symbol itself, which is just a 1 or 2 letter abbreviation for the for that particular element. So hydrogen is just H, helium is He, carbon is C, oxygen is O, and nitrogen is N. There's some weird ones that you wouldn't guess, like lead is Pb, because the old Latin word for lead was plumbium. So that's where Pb comes from. Potassium is K. Again, because the old Latin word for potassium is kalium with a K. One of my favorite ones is tungsten, is a W, because the old name, the old sort of Middle Ages name for tungsten was wolfrium. Anyway, so there's all these symbols for the elements. But then to the left of the symbol, in the bottom, we have the atomic number. So the count of the number of protons in the nucleus, which is what defines what kind of element it is. And then in the upper left is the mass number. So protons plus neutrons. So in this case, helium, we see that it has an atomic number of 2, so we know that it has 2 protons in the nucleus. It has a mass number of 4, so we already know it has 2 protons, so that means it must also have 2 neutrons as well. So 2 plus 2 gives us 4. Now, I said before that the number of protons doesn't vary, at least within a given element. If you're talking about carbon, it's always going to have 6. It's always going to have 6 protons in the nucleus. Otherwise, it wouldn't be carbon anymore. But the number of neutrons can actually vary. So the atomic number, which is a count of the number of protons, that's always going to be the same. The atomic number for carbon is always 6. But the number of neutrons may vary. So that means that the mass number can be a little bit variable, and we still call it carbon. So for example, there are actually 3 common forms of carbon. There's carbon-12, carbon-13, and carbon-14. The ones you hear about most frequently are carbon-12 and carbon-14. And so that little 12 in the upper left in carbon-12 means that this is kind of the typical normal form of carbon. So carbon has an atomic number of 6, so it has 6 protons in the nucleus. And carbon-12 has a mass number of 12. Remember, that's the number of protons and neutrons added together. So that means carbon-12 must also have 6 neutrons. So 6 protons plus 6 neutrons gives us a mass number of 12. But then there's this other form of carbon called carbon-14, which has 2 additional neutrons. Again, the number of protons always stays the same. That's not going to change. But carbon-14 has 2 extra neutrons. So 6 protons plus 8 neutrons gives us 14. Those extra neutrons in the nucleus of carbon-14 make it radioactive. Over time, those extra neutrons will come flying out of the nucleus. And those neutrons just kind of flying around randomly in space can actually be damaging. That's one of the reasons that radiation is bad for people, because these little particles can actually damage things like your DNA, causing mutations, and cause other kinds of injury. Carbon-14 is not highly radioactive. It's not like uranium or plutonium or something like that, but it's a little bit radioactive. And it undergoes a process called radioactive decay, which is where it gradually loses those extra neutrons and eventually decays from carbon-14 down to carbon-13 by giving off 1 neutron. And then carbon-13 can decay to carbon-12 by giving off the other extra neutron. And then by the time it reaches carbon-12, it's not radioactive anymore. It's stable, and it's just going to remain as carbon-12 pretty much, forever. Another example, a much larger atom, much larger element that has a much larger atomic number and a much larger mass number is uranium, which probably all know is a very highly radioactive metal. Uranium always has 92 protons. Otherwise, it wouldn't be uranium. So we say it has an atomic number of 92. But then, in addition to the 92 protons, it can have either 143, 146, or 147 neutrons. Add that to the 92 protons, and you get three different mass numbers. You can have uranium-235, uranium-238, or uranium-239. They're all actually radioactive, but the ones with the higher mass numbers are more radioactive. And uranium-238 was the form of uranium that was used in one of the bombs that was dropped. I forget if that was the Hiroshima or Nagasaki one, but it was one of them. There was one bomb called Fat Man and another one called Little Boy. One of them used uranium, the other one used plutonium. These isotopes give rise to a couple of important concepts. I already mentioned this idea of decay, where one of these radioactive isotopes over time gradually gives off its extra neutrons. That's the process called radioactive decay. And the half-life of a radioactive material is the time that it takes for half of the atoms to decay. So you start out with, a kilogram of uranium, and it takes so many, I don't actually know off the top of my head what the half-life of uranium is, but after so many thousand years, half of those uranium atoms have decayed to a different form. And then after another half-life, another so many thousand years, half of what's left has decayed. They don't all decay at once. They don't all decay at the same rate. It's another one of these sort of random statistical things. Like in any given half-life, half of the atoms will have decayed, but half of them will still be radioactive. And then after another half-life, another half of what's left has decayed. And then again, half of what's left has decayed, and so on. Yeah.
How is it coming along with radioactive protons?
It's losing the neutrons, the extra neutrons. Yep. But particularly like with the example of carbon-14, right? It loses one neutron to become carbon-13, loses a second neutron to become carbon-12, and then it's stable. It's not radioactive anymore. So we use this concept of a half-life for radiometric dating. So if you know how much of a certain radioactive material was present in a specimen when that specimen was created, and now you measure how much of that radioactivity is left, if you know the half-life of that material, you know, okay, it took this many thousand years for it to have decayed down to this level. Carbon-14, I forget the exact number, but it has a half-life somewhere in the range of 1,000, 10,000 years, somewhere in that ballpark. And there's a general principle in radioactive decay, and not sure I could completely explain it. I learned it once and then promptly forgot. But you can use a radioactive material for radiometric dating for a range of dates anywhere from about 1/10 the half-life up to about 10 times the half-life. And I think the point is that if you try to date something that's like less than 1/10 of the half-life, not enough of it has decayed to really be able to measure it. If you go more than 10 times the half-life, there's so little of it left that it becomes hard to measure. But generally speaking, whatever the half-life is, you can use that to date things, in that range from about 1/10 to 10 times. So carbon-14 dating is used to date things, like in archaeological time, you can date things from the Renaissance, you can date things from caveman times, but you can't date things back to the dinosaur days. You have to have other kinds of radiometric dating, other things that have longer half-lives, to be able to use them to date things that are really, really old. One of the most common ones for dating things like from the dinosaur era is potassium argon dating. There's a radioactive form of potassium that breaks down into the gas argon over time. There's strontium 90. I think that's another one that has really long half-life. And then there's even a different kind of dating, which really has nothing to do with radioactive dating. Well, I guess it kind of does. There's something called fission track dating for dating things that are like the age of the Earth, like 4.5 billion years. All right, so getting back to some stuff that's probably a little bit more specifically relevant, to what you need to know as medical illustrators, talking about electrons and ions. So an atom, by definition, is electrically neutral, meaning it has no net charge, no total charge, either positive or minus or negative. Now, the electrons within that atom all have a negative charge of -1, and the protons in the nucleus all have a positive charge of +1. And so for an atom with no charge, it means that the number of electrons orbiting is equal to the number of protons in the nucleus. And so the number of negative charges of the electrons equals the number of positive charges of the protons in the nucleus. And so those charges cancel one another out. And so you end up with something that's electrically neutral. But under certain circumstances, an atom may gain electrons or they may lose electrons, in which case we call the atom now an ion. It's no longer just an atom, it's an ion. So it has a net charge. If you gain one electron, if an atom gains one electron, so it now has one more electron orbiting than it has protons in the nucleus. It has one more negative charge orbiting compared to the number of positive charges in the nucleus. It has a net negative charge of -1. You could also have 2 extra electrons or 3 extra electrons orbiting around the nucleus, in which case you'd have a charge of +2 or +3, or excuse me, -2 or -3. Did I say minus before when I said 1? There would be, yeah, I meant minus. So if you have an extra electron orbiting, you're going to have a charge of -1. If you have 2 extra electrons orbiting, you have a charge of -2. If you have 3 extra electrons, you have a charge of -3, right? So we have more negative charges orbiting, more electrons orbiting than you have positive charges in the nucleus. And in that situation, we would call that an anion, a negatively charged ion, where there are more electrons orbiting than you have protons in the nucleus. We call that an anion. Now, the opposite can also happen. An atom can lose electrons. If you lose one electron, you've gotten rid of one negative charge, but you still have all of those positively charged protons in the nucleus, so you end up with a net charge of +1. You lose 2 electrons, you end up with a charge of +2. If you lose 3 electrons, you end up with a charge of +3. These are all referred to as cations. So any positively charged ion is a cation. Something else that's very important about the electrons that are orbiting around the nucleus, and something that's going to be important for our understanding of atoms and bonding, is that the electrons are arranged into a series of layers or shells orbiting around the nucleus. The electrons are not all orbiting at the same distance away from the nucleus. There are some electrons that orbit very, very close to the nucleus, others that orbit a little bit farther away, and still others that orbit even farther and farther away. This is where, especially the grad students who've taken science or those undergrads who've had to take a bunch of chemistry, this is where you'll be very thankful that we're not going to get into hybridization of orbitals, because we don't need to get to that level to do what we need to do. But we do need to understand that the electrons fill these orbitals in a certain order. So that the innermost shell, the electrons that orbit closest to the nucleus, that shell or that layer can only hold 2 electrons. And that's going to fill up first before any electrons then start occupying the second shell. The second shell is a group of electrons that orbit a little bit farther away from the nucleus. That one can hold 8 electrons. It's farther away, so it's a bigger space, I assume. That's probably the reason why it can hold so many more. That holds 8 electrons. Then there's a third shell, which can also hold 8 electrons. And we don't really go beyond that. Most of the elements that we're going to deal with in this class can be described using just these first 3 shells. It does get way more complicated. You get up to something like uranium, which has so many, 92 protons in the nucleus. There's a lot of shells to accommodate all of the electrons that have to orbit around it. We're not going to get into any of those really, really big elements. So most of what we're going to talk about is going to be covered by just these three shells. Okay, so just remember, first shell holds 2, second and third shells hold 8 electrons. The inner ones are always going to fill up first before you find any electrons in the outer shell. So here's the arrangement of electrons in 4 of the most common elements that are found in all the big things. Organic molecules are sometimes referred to as hydrocarbons because they're made up largely of hydrogen and carbon, and then a handful of other things. So in the upper left is the structure of hydrogen. Hydrogen has an atomic number of 1, meaning it has 1 proton in the nucleus. Hydrogen actually doesn't have any neutrons in the nucleus. At least the normal vanilla version of hydrogen has no neutrons. There actually are versions of hydrogen that have neutrons. They're isotopes. There's something called deuterium and something called tritium that have multiple neutrons in the nucleus. But the normal run-of-the-mill form of hydrogen is literally, the nucleus is literally just a proton. So that 1 proton has a charge of +1. It has 1 electron represented by the little black dot orbiting in that inner shell. And so that hydrogen atom is electrically neutral because the 1 negative charged electron cancels out the positive charge of the 1 proton in the nucleus. Jumping up to carbon. Carbon has an atomic number of 6. So that means it has 6 protons in the nucleus. That means, at least if it's electrically neutral, it's also going to have 6 electrons orbiting the nucleus. So 6 negative charges canceling out 6 positive charges. The first 2 of those electrons are going to reside in that inner shell. And it's only after that inner shell is filled that the remaining 4 electrons then move out into the second shell. See, we got a shell, okay. Nitrogen has an atomic number that's just 1 bigger. Nitrogen has an atomic number of 7 instead of 6. That tiny difference, the difference of just 1 extra proton in the nucleus, makes all the difference in the world in terms of the bonding behavior of nitrogen and the geometry of the bonds that nitrogen forms. So atomic number of 7 means it's got 7 protons in the nucleus, so 7 positive charges, and then it's going to have 7 electrons orbiting. The first 2 are going to go in the first shell, and then you're going to find 5 electrons in the second shell. Oxygen has an atomic number of 8. 8 protons in the nucleus, 8 electrons orbiting. The first 2 in the inner shell, the remaining 6 electrons in the second shell. Some other elements that are things that you'll encounter pretty frequently when you're illustrating biological processes, things like sodium and potassium, which are the primary atoms or ions that pass through the cell membrane to create an action potential in a neuron. Calcium in the bottom right is what's responsible for muscle contraction by binding tropomyosin on the actin thin filament. Calcium is also an important ion in the release of neurotransmitters in the synapse. So these are other, phosphorus is hugely important. The P up here is phosphorylation of proteins is an important way of activating a protein. Phosphorus is part of ATP, adenosine triphosphate, the main energy molecule in the cell. So these are all important things. So Na is sodium. I don't think I told you that obscure Latin thing before. The old Latin name for sodium was natrium, hence the Na symbol. Has an atomic number of 11, so 11 protons in the nucleus, 11 electrons orbiting, at least in the neutral, the electrically neutral form of sodium. So there are going to be 2 electrons in the first shell, 8 in the second shell. Now that second shell is filled as soon as it has 8 electrons in it. So any remaining electrons now have to jump out to the third shell. So 2 in the first shell, 8 in the second shell, that's 10. So that means we got 1 lone electron orbiting way out there in that third shell. Phosphorus with an atomic number of 15. It's going to have 2 electrons in the first shell, 8 in the second shell, that's 10. So the remaining 5 electrons are going to be in the third shell. Potassium, K, used to be called kalium, atomic number of 19. So we've got 2 electrons in the first shell, 8 in the second shell, that's 10. 8 more in the third shell, that's 18. So once again, we have 1 lone electron out here, but now it's out in a fourth shell. And calcium, an atomic number of 20. There are 18 electrons in the first 3 shells, and then 2 more in the second shell for a total of 20. The presence of these different shells of electrons, as well as the number of electrons that are found in that outermost shell, whatever the outer shell is, whether it's the first shell, second or third or fourth, whatever the biggest or outermost shell is for that atom, that's the basis for the creation of the periodic table. And there was a Russian chemist, Mendeleev, who was the one who first developed the periodic table, using this information. Now, what I've drawn here for you is a very simplified version of the periodic table based on the information that I just gave you, that you have different numbers of electron shells, and then whatever the outermost shell is going to have a certain number of electrons in it. So the horizontal rows represent the different electron shells. So the very top row represents that very first shell, that innermost shell that can only hold 2 electrons. Then after that first shell is filled, if you have any additional electrons, they're going to reside in the second shell. So here we have shells 1 and 2. And so everything in this second row has 2 shells. It has the first shell and then the second shell. And then once that's full, if you have additional electrons, they're going to jump out into the third shell. And so everything in this third row is going to have 3 shells. It's going to have the small inner shell, it's going to have the second shell completely full, and then it's going to have electrons in the third shell, and then the fourth shell, and so on. Now, the current periodic table gets a lot more complicated than that, because you get into these different groups of elements called actinides and galanthanides that have very different behavior, and it's no longer limited just by these shells. But if you look at just the first couple of rows of the periodic table, it's actually relatively simple. So like I said, the horizontal rows just tell us how many shells are present, 1, 2, 3, or 4, or more shells. The vertical columns represent something different. The vertical columns tell us how many electrons are present in the outermost shell. whatever that outermost shell is, whether it's the first one, second one, third one, fourth one, whatever, how many electrons are present in that outer shell. So this first column over here, labeled number 1, everything in this first column has 1 electron in its outer shell. So hydrogen only has 1 electron, and it's in the inner shell, but that for hydrogen, that's the only shell there is. So that's the outermost shell for hydrogen. Lithium, the inner shell is full, and there's 1 electron in the second shell. Sodium, 2 electrons in the first shell, 8 electrons in the second shell, so those 2 are full. So the 11th electron sits all by itself in the third shell. Potassium has the first 3 shells are full, and then 1 electron in the fourth shell. The second column are things that have 2 electrons in the outer shell. Now, if we look over here at helium in the upper right, helium has 2 electrons in its outer shell. But remember that that smallest shell, that innermost shell, only holds 2 electrons. So we actually lump helium over here at the far right because its outer shell is full. So the far right-hand column represents elements in which, regardless of what shell it is, whether it's the first, second, third, fourth, it's a completely full shell. Right, so going back to our other columns, with 2 electrons in the outer shell, we've got beryllium, magnesium, calcium. 3 electrons in the outer shell, boron and aluminum. 4 in the outer shell, carbon, silicon. Turns out that carbon and silicon have some very similar chemical properties because they both have 4 electrons in their outer shell. There are other elements that fall below here. I know the next one down is called germanium, which is very commonly used in like making computer chips. Nitrogen, phosphorus both have 5 electrons in the outer shell. Oxygen and sulfur have 6. Fluorine and chlorine have 7. And then you get bromine and iodine also are in this same column, all having a single electron, or excuse me, 7 electrons in their outer shell. I'm not going to show you this link, but if you want to go check this out, one of our alumni, I haven't checked this recently to see if this still works, but one of our alumni who used to work for Science Magazine created a really nice infographic about the history of the periodic table. Right, so the next thing I want to talk about is I want to use all of this information about the presence of electrons in these various shells to try to understand atomic bonding. How do bonds form between neighboring atoms? And the bonding of atoms all depends on a fairly simple, straightforward principle. I'm not sure I can explain why this is true, but it's not a hard concept to understand. Atoms like to have their outermost shell full. Now, obviously, atoms don't like anything. They don't like ice cream. They have no mind or soul or preference. So when I say that atoms like to have their outermost shell completely filled, it just means that that's the most energetically stable configuration. When an atom does not have a full outer shell, it's less stable, and it tries various tricks to try to fill up that outer shell, because that would be a more energetically stable configuration. Now, there are 3 different ways that an atom can achieve that stable state, where it can fill up its outer shell. One way to do that would be to steal electrons from another atom, to just yank some electrons away from another atom, fill up any remaining holes in your outermost shell, and then this atom is happy. But by doing that, by stealing electrons, that atom now has more electrons orbiting than it has protons in the nucleus. So that means it ends up with a net negative charge. Might be a negative charge of -1, could be -2, could be -3. we would call it an anion at this point because it's now a negatively charged ion. Another way that an atom can fill its outermost shell is to actually give away electrons. And we'll talk about this more in a minute, but this is most common for any atom that has very few electrons in the outermost shell. It's more than happy to give away those 1 or 2 or 3 electrons in the outermost shell. Now it's getting rid of its outermost shell, but what that means is that the next shell down, the next deeper shell, is completely full. So this still satisfies this same condition that what becomes its outermost shell is now completely full, so it's energetically stable. So when an atom gives away electrons, it still has the same number of positive charges in the nucleus, but now it has fewer negative charges orbiting. So that means it ends up with a net positive charge. So we would call that a cation. It's a positively charged ion. And then finally, the third way that atoms can fill up their outermost shells is for 2 atoms to get together and actually share electrons. So from one atom's point of view, it looks like their outer shell is full. From the other atom's point of view, it looks like their outer shell is full, even though some of those electrons are being shared between the 2 of them. Now, there are some elements on the periodic table that, under normal circumstances, don't ever form bonds. And these are the ones at the far right of the periodic table, the ones that have a full outer shell. And that's why helium gets stuck over there on the right, because even though its outer shell only has 2 electrons, it's full. So these elements are completely stable under normal conditions. They have a full outer shell. They have no reason to steal electrons. They have no reason to give away electrons, and they have no reason to share electrons. I see a hand up there. You can make these things bond in a laboratory under extreme conditions. So that's why I say under normal circumstances, these things never bond. But it has been done. People have made these so-called inert elements actually not inert anymore. But I don't know exactly what they do to them. I don't know if it's under crazy high temperature or some kind of electrical stimulation or something like that, or crazy high pressure. I don't know exactly what it is. But you've got to do something pretty dramatic to get these things to make bonds. But, you know, normal just helium floating around in our atmosphere is never going to make a bond. Right? So helium has a full outer shell of 2 electrons. Neon has both the first 2 shells filled, the second shell filled with 8. Argon has all 3 shells full. There's a couple others. There's krypton, radon, keep going down the periodic table, and there's more. I forget what the rest of them are. So these are known as inert elements. Another term that's often used for them is these are the noble gases. Not Nobel like the prize, but noble like dignified. Or I don't, it seems kind of a silly name for me. I just call them the inert elements. And they're all gases. Even krypton, radon, even though the atoms themselves get very big, they exist in a gaseous state. I guess because they don't bind to anything. All right, so I mentioned that one way that atoms can become electric or can fill up their outermost shell is by either stealing or gaining electrons. That's the basis for what we call ionic bonding. It's one way that atoms stick together. It's by forming these ionic bonds. So what happens in an ionic bond is that you've got one atom which is a donor. One atom gives up either one electron or multiple electrons. And remember, if it gives away electrons, it still has the same number of positive charges in the nucleus, so it ends up with a net positive charge. Might be +1, +2, +3, but it's going to be a positive charge, so we'd call it a cation. Then there's some other atom that needs to fill up its outer shell, and it's more than happy to be the recipient of those extra electrons. So this other atom receives the electrons. It now has more negative charges orbiting than it has positive charges in the nucleus, so it ends up with a net negative charge. So we would call it an anion. So you end up with a cation with a positive charge, anion with a negative charge. These two ions are now attracted to one another because things with opposite charges are attracted to one another. So the positive charge and the negative charge are attracted, and that holds these atoms together. That's an ionic bond. So here's an example of an atom that loves to give away an electron. There's sodium with an atomic number of 11. So that means it's got 11 protons in the nucleus. It's got, in its electrically neutral form, it has 11 electrons as well. 2 in the first shell, 8 in the second shell, that's 10. And then the 11th electron all by itself in that outer shell. And so sodium is unhappy because it's got this one electron in that outermost shell. And boy, if it could just get rid of that one electron, then the next shell down would be completely full. So sodium happily gives away an electron, completely empties out its third shell, but now the second shell is completely full, so it's energetically stable. But by giving away one negative charge, it still has 11 protons in the nucleus and only 10 electrons. That means it ends up with a charge of +1. So when you see sodium represented as an ion, it's always Na+ with a single positive charge. So it's a cation. And going back to our periodic table, the things that sit over near the left are atoms that are likely to give away electrons because they have relatively few electrons in their outer shell. It's much easier for them to give away 1 or 2 or 3 electrons than it is to steal 5 or 6 or 7. So everything in the far left column has just 1 electron in the outer shell. So that means hydrogen, lithium, sodium, and potassium all form cations with a single positive charge. Na+ for sodium, K+ for potassium. In the next column, we have atoms that have 2 electrons in their outer shell. They will happily give away those 2 extra electrons to have a charge of +2. So you don't see beryllium very often in biological systems, but magnesium is a pretty common ion, and it has certain roles in the body. And it's always Mg either ++ or Mg2+ to represent the double positive charge. And calcium, as I said, that's a very common one in biological systems because it's responsible for things like muscle contraction and release of neurotransmitter vesicles. And that always is also Ca++ or Ca2+ with a double positive charge. Boron and aluminum have 3 electrons in their outer shell. You don't see these too often in biological systems, but they will give away those 3 electrons to become either a B3+ or aluminum 3+ cation. So then you have other atoms that are more than happy to receive extra electrons to fill up their outer shell. So here's the example of chlorine. Chlorine has an atomic number of 17. So there are 17 protons in the nucleus. And in the electrically neutral version, there are 17 electrons orbiting. So 2 in the first shell, 8 in the second shell, that's 10, 7 in the third shell. So we got a total of 17 electrons. So it's electrically neutral, but it's unhappy. It's unstable. It really needs an extra electron to fill up that outermost shell to be stable and to be happy. So it's going to accept an electron from some donor, like from sodium, for example. And so now this chlorine, or we'd actually call it the chloride ion. I don't know why for chlorine and bromine and iodine, when it becomes an ion, change the name of it so it becomes chloride, iodide, bromide. So now we've got 18 electrons and only 17 protons in the nucleus, so it has a net charge of -1. Yeah. It just flies off and finds another one. I mean, that's an oversimplified explanation, but
Side.
well, because if it has one extra or one, like just one in its outermost shell, like the sodium example I just gave a few minutes ago, that's energetically unstable. If you want to know more about that, learn quantum mechanics. That's my explanation. Go read The Nature of the Chemical Bond by Linus Pauling, that was published in like 1930 something.
Best friends for 6 majors.
Yeah. Linus Pauling's one of my heroes. I'm going to talk about him about 6 times in this class. This is my first reference to Linus Pauling. I'll talk about him again before the day is over. But he was a physicist or chemist. I don't know. He was kind of on the borderline between physics and chemistry. He spent pretty much his entire career at Caltech. And he took a sabbatical and actually spent a year, maybe 2 years. No, I think it was just a year at Cornell on sabbatical. And during that time, he wrote this book called, it was called The Nature of the Chemical Bond. And won his first Nobel Prize. First 2. And basically he had visited Werner Heisenberg and Erwin Schrödinger and Niels Bohr and all the big names in quantum mechanics, that the folks over in Germany and the Netherlands, like during the 1920s and early 30s, the people who were coming up with quantum mechanics. He went and visited them, did like, I don't know, a fellowship or something, working and studying with them, and then, came back and basically used the principles of quantum mechanics to explain chemical bonding. And so my statement that atoms like to have their outermost shell full is an extreme oversimplification of what Linus Pauling took an entire book to explain. All right. So here we have the formation of an anion, some atom that has a lot of electrons in its outer shell and needs just 1 or 2 or maybe 3 to fill up that outermost shell. So it will happily accept electrons from some donor. And this is particularly common among the elements that sit kind of near the far right-hand edge of the periodic table. Remember, they're not going to be the ones all the way at the far edge, because these have full outer shells, so they're completely stable the way they are. But things like fluorine, chlorine, bromine, iodine, these things all have 7 electrons in their outer shell, so they're more than happy to accept one from a donor, like from sodium or potassium or something like that. Oxygen and sulfur have 6 electrons in their outer shell. They will happily accept 2 electrons to fill up their outer shell and end up with a charge of -2. And nitrogen and phosphorus have 5 electrons in their outer shell, so they need 3 additional electrons to fill up their outer shell. So they will happily accept those 3 and end up with a charge of -3. So here is the process of formation of an ionic bond between sodium and chlorine. So we've got sodium with that atomic number of 11, having just one electron in its outer shell. It really wants to give that away so that then the next shell down is completely full. So it happily gives away one electron and ends up with a net charge of +1. Chlorine has 7 electrons in its outermost shell. It really needs one more to fill up that outer shell. And so it happily accepts that donated electron from the sodium. The chloride ion ends up with a net charge of -1. And I just realized, oh, I know what I did. I got to fix this slide someday. I just realized 2 of my dots got moved. This should have a completely full outer shell, but 2 of the dots somehow got slid over by accident in this picture. But so you end up with a sodium cation with a charge of +1. You've got a chlorine anion with a charge of -1. Those opposite electrical charges attract one another, and so these things stick together. And that's salt, table salt. All right, why don't you take a short break and come back and talk about atoms sharing electrons to create a different kind of bond. So why don't you come back? Please be back by 20 after, by 3:20. I will start promptly at 3:20, just in the interest of time. All right, so I've talked about ionic bonding, where one atom gives up electrons. Shoot, that thing is in the way. Let me stop the share for a second. Sometimes the screen here has the Zoom thing in the way. So I have to go to PowerPoint, get out of full screen mode, go back here. Let's try this again. Okay, that worked. Now I don't have Zoom in the way on the projector here in the classroom. All right, so I talked about ionic bonding, where one atom gives away an electron and becomes positively charged. Another atom receives the electrons to become negatively charged, and then those opposite charges attract, forming what we call an ionic bond. In a covalent bond, rather than donating or stealing electrons, atoms share electrons equally. And they have to share pairs of electrons. They can't just share one. It's always going to be a pair of electrons that are shared. And they can share one pair, which we would call a single bond. They can share 2 pairs of electrons, which we would call a double bond, or they can even share 3 pairs of electrons to form a triple bond. And I don't think there's anything more than a triple bond, covalent bond. Any atom anywhere on the periodic table, other than the inert elements in the far right column, any other atom besides those inert elements can form a covalent bond, regardless of where it sits on the periodic table. So with ionic bonding, I mentioned that the atoms at the far left of the periodic table are more likely to become positively charged cations by giving away electrons. The ones that near the right, like especially in column 7, are likely to receive electrons and become anions. But any element anywhere, any atom anywhere on the periodic table, except for the inert ones, can also form covalent bonds. But covalent bonding is especially common among the elements near the middle of the periodic table. Because if you're sitting near the middle of the periodic table, it means you've got a bunch of electrons in your outer shell, and it may be very hard to give them away, or it may be very hard to steal the ones that you need. It may be easier to simply share electrons. So I already mentioned that if 2 atoms share a single pair of electrons, that is considered a single bond. Even though it's a pair of electrons, it's one bond. If you share two pairs of electrons, it's a double bond. If you share three pairs of electrons, it's a triple bond. So the elements at the center of the periodic table are the ones that are most likely to form covalent bonds. So carbon and silicon both have 4 electrons in their outermost shell. Well, to fill up their outermost shell, they're either going to have to give away all 4, or they're going to have to steal 4. And neither of those options is particularly favorable from an energy standpoint. So carbon and silicon essentially never form ions, but they will form covalent bonds very readily. And the other elements on here, like I said, they can also form covalent bonds, but they may be more likely to form ionic bonds. In chemistry, there are a few different ways to depict the sharing of electrons and to depict covalent bonding between atoms. And there are 3 different ways of representing bonded atoms here. At the top, we actually see these little orbital diagrams that I've been showing you all along, where we actually see the arrangement of the electrons. We see the electrons in the outermost shell of the atoms, and we can see that multiple atoms are actually stuck together because of the way they share a pair of electrons or multiple pairs of electrons. So here in the upper left is a diagram, a representation of a water molecule. So we have an oxygen atom in the center, which has an atomic number of 8. So that means it has 8 protons in the nucleus and 8 electrons orbiting. The first 2 electrons are going to be in the first shell. The remaining 6 electrons are going to be in the second shell. That means that that oxygen atom is missing 2 electrons in that second shell in order to fill it up. Really wants 2 more to fill up that second shell. Hydrogen, with an atomic number of 1, has just a single proton in the nucleus and has a single electron orbiting the nucleus. In order for hydrogen to be stable, it could either give away that 1 electron, or it can share an electron with another atom and therefore have 2 electrons in its shell, and therefore that inner shell would be full. So what's happening here is that on the left, we have a hydrogen atom, which is sharing its own electron and sharing one of the oxygen electrons to create a pair. So that pair of electrons is being shared equally by the hydrogen and the oxygen. Actually, I shouldn't say that. Not necessarily shared equally. There may be an imbalance in how those electrons are shared, but they are being shared. Not necessarily equally, but they are being shared. So this pair of electrons is being shared by the hydrogen and the oxygen. That creates a single covalent bond between the hydrogen and the oxygen. Over on the other side, we have another hydrogen atom, which is also donating one of its electrons to this pair, and the oxygen is donating electron to another pair over here. So here's a pair of electrons being shared by the oxygen and the hydrogen. So that's another covalent bond. It's a covalent bond between the oxygen and a second hydrogen. So we've got oxygen in the middle, covalently bonded to 2 hydrogen atoms, and the oxygen is sharing a pair of electrons with one hydrogen and sharing a different pair of electrons with the other hydrogen. Now, if we count up the electrons, we should be able to tell that the oxygen still only has 6 of its own in the second shell. So it's got 2 up at the top, 2 down at the bottom, that's 4. 1 of these in this pair on the left belongs to the oxygen. 1 in the pair on the right belongs to the oxygen. So that is a total of 6 electrons that quote unquote belong to the oxygen atom. And likewise, there's 1 electron that belongs to this hydrogen and another electron that belongs to the other hydrogen. But as far as all 3 of these atoms are concerned, they all feel like they have full shells. The hydrogen kind of looks outside and says, oh, I've got 2 electrons in my outer shell, even though those are both being shared with the oxygen. The oxygen atom looks at its outer shell and says, oh, I've got 8 electrons in my outer shell, even though 2 of them are being shared with hydrogen. A different way to depict that is what's called the Lewis figure, or a Lewis dot figure. And in a Lewis figure, you ignore any electrons in the inner shells. So you would ignore the 2 electrons in this innermost shell of the oxygen. You only represent the electrons in the outer shell of the oxygen, as well as the shell of the hydrogens. So you see there are 6 dots here around that oxygen in the middle. Now, 2 of those at the top here belong entirely to the oxygen. 2 down here at the bottom belong entirely to the oxygen. This pair of electrons on the left, one of those belongs to the oxygen, one belongs to the hydrogen. Same thing over here on the right. One belongs to the oxygen, one to the hydrogen. So that's a shared pair, or what we call a bonding pair. And there's another shared pair or another bonding pair over here on the left. And then the way of visualizing these bonds that you're probably most familiar with is to just create a stick figure where you simply draw a black line between the atoms to indicate the presence of a bond. But keep in mind that this stick figure is not showing you the whole story. Each stick actually represents not just 1 electron, but a pair of electrons that are being shared. That makes a single covalent bond. The other thing that you don't see in a stick figure like this is you don't see that there are other electrons on that central oxygen that are not being shared, that are not participating in the bonds. And that's going to turn out to be really important later. Here's another example. This is nitrogen gas. Nitrogen has an atomic number of 7. So if we look at just a single nitrogen atom, it's going to have 7 protons in the nucleus, 7 electrons orbiting. 2 of those electrons are in the first shell, but then 5 are in the second shell. Now, 2 of them are over here on one side, but we've got 3 of its electrons are being shared with another nitrogen. Same thing with the other nitrogen. It has 7 electrons, 2 in the first shell, 5 in the second shell. 2 of them are over here just chilling, but then 3 are being shared. So these 2 nitrogen atoms are actually sharing 3 pairs of electrons. We would call that a triple bond, with each pair of electrons being shared is a single covalent bond. So in our Lewis dot figure, we'd represent it like this here, with 3 pairs of dots between the 2 nitrogens, indicating that they're sharing 3 pairs or 6 electrons total, as well as some additional electrons that are just kind of chilling on the nitrogen and not being shared. And then if we represent it just as a series of sticks to represent the bond, you see that we've got a triple bond, 3 lines. So let's talk about the arrangement of electrons in the common organic elements, things like carbon, nitrogen, hydrogen, oxygen, and the kind of bonds that they form. So here's hydrogen, which is the most abundant element in all living tissue, all living things. Not by mass necessarily, but just by sheer number of atoms. This is the most numerous atom found in living things. And here we see its electrically neutral form on the left. And it's got a proton in the nucleus. It's got a single electron orbiting. So those charges cancel out. So this hydrogen atom is electrically neutral. But the hydrogen is not too happy. It really wants to fill up that first shell. And believe it or not, one way to fill up its shell is to actually just get rid of its electron altogether. It doesn't even have a shell now, but it's perfectly happy to do that. It's energetically stable to just give away its only electron. So you're left with literally a proton. And sometimes in biology and in chemistry, they'll refer to the hydrogen nucleus, the hydrogen ion, as literally just a proton. Like, for example, in the production of ATP in the mitochondria, there's something called a proton pump, a proton gradient. It's actually referring to a gradient of hydrogen ions, H plus, which are literally just protons. So this hydrogen could then form ionic bonds with negatively charged ions. But hydrogen also participates in covalent bonds. Now it's only got one electron in its outer shell. That means it can only ever form one bond. So hydrogen can only be bonded to one thing at a time. You'll never see hydrogen bonded to two things. Always going to be bonded to just one other thing. So hydrogen forms just one bond, whether it's a single ionic bond or whether it's a single covalent bond. So in the case of water, the oxygen is forming two bonds, but it's forming one bond with one hydrogen and one bond with another hydrogen. So hydrogen always forms one bond. Oxygen always forms two bonds. So here's the electrically neutral form of oxygen, atomic number of 8. So 8 protons, 8 electrons. The first 2 electrons are in the inner shell, leaving 6 in the outer shell. And from an energy standpoint, the easiest way for oxygen to fill up that outer shell is to steal 2 electrons. It steals 2 electrons, it fills up that outer shell, and it ends up with a charge of -2. Oxygen can also form covalent bonds, and it will always form 2 covalent bonds. Now, it could be 2 single bonds, as in the case of water, or it could be 1 double bond, as in the case of oxygen gas, O2. But it's still a total of 2 bonds. So either 2 single bonds or 1 double bond. So let's take a look at the water molecule again, looking at it from the perspective of the oxygen in the middle. It's got 6 electrons of its own, and it's sharing a pair with hydrogen, sharing another pair with a different hydrogen, so forming a single covalent bond with one hydrogen and forming a covalent bond with the other hydrogen. So 2 single bonds. In oxygen gas, the 2 oxygen atoms are sharing 2 pairs of electrons. So as far as, if we look at this oxygen on the right here, when that nucleus is looking out, it says, okay, I've got those 2 electrons, I got those 2, that's 4. I'm sharing 4 more. So as far as this oxygen is concerned, it's got 8 in its outer shell. Same thing with the oxygen, so it's energetically stable. The oxygen is happy. So those 2 shared electrons, or 2 pairs of shared electrons, represents a double bond. So this is the oxygen gas that we breathe, which makes up about, 18% of the Earth's atmosphere. So the key point here, though, is oxygen forms 2 bonds because it's missing 2 electrons in its outermost shell. It needs to fill that up. So it can form either 2 single bonds or 1 double bond. Nitrogen always forms 3 bonds. Nitrogen has an atomic number of 7. 7 protons in the nucleus, 7 electrons orbiting. The first 2 electrons are in the first shell, and then 5 in the second shell, meaning it has basically 3 empty spaces in its second shell. And there are a couple of ways that it can fill up that second shell. It could steal 3 electrons from somebody else, and at this point we now call it a nitride ion. Because you've stolen 3 electrons, you now have a net charge of -3. This is pretty rare. You don't see this represented very often, but it can happen. Instead, nitrogen more typically forms covalent bonds, and it's going to form 3 covalent bonds. So in the bottom left is a molecule called ammonia, NH3. So it's a nitrogen bonded to three hydrogens by three single bonds. So here's the Lewis dot structure. We've got a pair of electrons being shared by the nitrogen and one hydrogen, a pair of electrons being shared by the nitrogen and a second hydrogen, and a third pair of electrons being shared by the nitrogen and a third hydrogen. But then there's another pair of electrons up here on the nitrogen that are just chilling out, that are not participating in the bond. And again, we'll come back to that because that's important. So you could do a little stick figure of ammonia with nitrogen in the center with single bonds to three different hydrogens. Here's a different nitrogen compound, hydrogen cyanide, pretty deadly poison. In this case, the nitrogen is triple bonded to a carbon. And then the carbon is forming a fourth bond with a single hydrogen. But so that carbon and nitrogen are sharing three pairs of electrons, hence a triple bond. So nitrogen always forms three bonds. Carbon, the last of the really common organic elements, is always forms four bonds. And carbon by itself basically never forms an ion. You never see carbon 4-. Now, carbon can join with other things to make ions, like the bicarbonate ion is HCO3, HCO3 minus. So carbon can join with other things to make ions, but carbon, a carbon atom by itself, you're never going to see that in the form of an ion. Carbon has an atomic number of 6, so 6 protons in the nucleus, 6 electrons orbiting, 2 of them in the inner shell, and then 4 electrons in the second shell. So the reason you almost never see carbon ions, I mean, I've never seen it depicted anywhere, is that it's really hard to steal 4 electrons and it's really hard to give away 4 electrons. So instead, carbon almost always forms covalent bonds. At least in biological molecules, you'll only ever see it in a covalent bond. So here are several examples of carbon compounds. In the upper right is CH4 or methane gas. It's a flammable gas. We got carbon in the very center bonded to 4 hydrogens. So it's sharing a pair of electrons with one hydrogen, sharing a pair with another hydrogen, sharing a pair with another hydrogen, sharing a pair with a fourth hydrogen. One thing to notice here is that all of the electrons around that central carbon are being shared. None of them are just chilling by themselves like they do in oxygen or nitrogen. And again, we'll come back to that in a minute. So methane would be represented as a little stick figure as carbon bonded equally to 4 hydrogens around it. Here's carbon dioxide down in the bottom left. We've got a carbon in the center with 2 oxygens on either, or 1 oxygen on either side. And it's sharing a pair of electrons with 1 oxygen, sharing another pair of electrons with another oxygen. So it's forming a double bond with 1 and a double bond with another oxygen. Notice again that all 4 of the electrons around that carbon are being shared. 2 pairs with 1 oxygen, 2 pairs with another oxygen. Here's another one I put in just to show that carbon can also form triple bonds. This is acetylene used in cutting torches, blow torches. So the 2 carbons are sharing 3 pairs of electrons, so that's a triple bond. And then each carbon is also forming a single bond with these 2 hydrogens on either end. So once again, total of 4 bonds. So carbon always forms 4 bonds. So what I've been talking about so far is the concept of valence. The definition of valence is that it's the number of bonds that an atom forms, or the atoms of a particular element. And the valence is determined by the number of electrons in the outer shell. But the definition of valence is simply the number of bonds that a particular atom or a particular element will form. Now, especially for my students who've had a bunch of chemistry before, they often get confused if I quiz people about this or if I ask them about it. There are two very similar sounding things that are closely related, but they're different. There's the term valence, and then there's the term valence electrons. Valence electrons refers to the number of electrons in the outermost shell. And that's going to control how many bonds an element forms, but it's not the same thing. So valence is simply how many bonds the atom will form. Now, for something like carbon, these numbers are the same. Carbon forms 4 bonds, so it has a valence of 4. Carbon has 4 valence electrons in the outermost shell, but it has 4 empty spaces. But then for the other atoms, it doesn't work that way. So nitrogen has 5 electrons in its outermost shell, so it has 5 valence electrons. But that means it only has 3 empty spaces in its outer shell, so it only forms 3 bonds. So the valence of nitrogen is 3. Oxygen has 6 valence electrons in its outer shell, but that means it has 2 empty spaces, so it only forms 2 bonds. So the valence of oxygen is 2. All right, next thing I want to talk about is how all of this stuff also determines the geometry of bonds, the angles between bonds. So if you think back to some basic math, basic geometry from a bygone era, from, I don't know, maybe high school or maybe before that. In order to have an angle, you need 3 points in space. And those 3 points are going to form 2 lines. And where those lines intersect, there's going to be an angle between those lines. So you see that down here on the bottom left. We've got points A, B, and C. You can draw a line from point A to point B. That creates 1 line. You can draw another line from point B to point C. And those 2 lines then are separated from one another by an angle. And we would call that angle ABC. Point B is what we call the vertex of the angle. It's the corner, the point. And this is very important in chemistry because if you have 2 bonds that are connected to the same atom, there's an angle that's formed between those bonds. So in chemistry, we have a similar situation here where we've got 3 atoms, and we could call that atom A at the top, atom B on the left, and atom C on the bottom. There's a bond between atom A and atom B, and another bond between atom B and atom C. And there's an angle formed between those 2 bonds. We're going to find out in a minute, I think on the next slide, that one of the main things that determines that angle is the arrangement of electrons on the central atom, the atom that sits right here at the corner point, the vertex of the angle. The arrangement of electrons around that central atom is going to dictate what that angle is. Well, like I just said, the angle between 2 bonds, that bond angle is determined by the electrons present on the central atom, the atom that sits at the vertex of that angle, at the intersection of those 2 bonds. Some other things that are going to determine this geometry is the basic principle that electrons, especially pairs of electrons, are going to repel one another. So the electrons that are involved in creating these bonds, these pairs of electrons that are shared to create covalent bonds, those electrons are going to try to push one another apart. Because all electrons have a negative charge. Things with identical charges tend to repel one another. So those pairs of electrons are going to try to push one another apart. Those bonding pairs that are helping to attach the atoms to one another. They're going to try to repel one another. But remember, I mentioned that some atoms have extra electrons that are just kind of chilling on that atom, like nitrogen. It's always going to have a pair of electrons that aren't participating in a bond. Oxygen is always going to have two pairs of electrons that aren't participating in a bond. Those are known as lone pairs, as distinct from bonding pairs. And I'll go over this again in a second on the next slide. I'll talk about this in more detail. But so a bonding pair of electrons are electrons that are actually participating in creating a covalent bond. Lone pairs are extra electrons that belong to an atom that are not participating in a bond. For whatever reason, and I don't understand the physics or the quantum mechanics about this, but lone pairs actually push harder than bonding pairs. And this also influences bond angles. So here's what I mean when I talk about lone pairs and bonding pairs. So there's our water molecule again. We've got oxygen in the center. And what I just mentioned on the previous slide is that the arrangement of electrons around that central atom, that's one that sits right at the corner, the vertex of the angle, that's the main thing that's going to determine the angle between these two covalent bonds. So we've got a bonding pair shown in red. That's a pair of electrons that's being shared by the hydrogen and the oxygen. So that's forming a covalent bond. We've got another bonding pair on the other side. This is a pair of electrons being shared by the oxygen and the other hydrogen. But then the oxygen in the middle has two lone pairs. There's a pair of blue dots up here, which is a lone pair, and a pair of blue dots down here, which is a lone pair. Here's the ammonia molecule that I showed you earlier, NH3. The nitrogen in the center has a bonding pair that's forming a bond with one hydrogen. It has a bonding pair forming a bond with a second hydrogen, and another bonding pair forming a bond with a third hydrogen. But that nitrogen also has one lone pair of electrons shown here in blue. These are the ones that are just chilling, that are not actually forming a bond. Carbon never has lone pairs. Mentioned earlier that all of the electrons around that carbon atom are participating in bonds. So in this case, these two carbons are sharing three pairs of electrons with one another to create a triple bond. And each carbon is sharing a pair of electrons with a hydrogen at either end of this molecule, and that's acetylene again. And down here is methane, CH4. Once again, if you look at the carbon in the center, it's got a bonding pair with one hydrogen, a bonding pair with a second hydrogen, bonding pair with a third hydrogen, a bonding pair with a fourth hydrogen, and no lone pairs. And that's going to really dictate geometry. So I'm going to walk through a couple of examples of bonding geometries or bond angles where the atom in the center has no lone pairs of electrons. Now here's one that doesn't exist very often in biological molecules, but there are a few. I kind of had to go searching to find some examples of molecules that have this configuration. But this is what's known as a linear geometry. So if you remember our picture of the angles where we have 3 points, A, B, C, we've got A over here on the left, we got B in the middle, and we got C on the right. So that's forming two bonds. We got a bond between A and B, we got another bond between B and C, and there's an angle between those two bonds. But in this case, that angle is 180 degrees, meaning this molecule is perfectly straight. All three atoms lie in a perfectly straight line. And here are some examples. Mercuric chloride or mercuric dichloride. We've got a mercury atom in the middle, and I forget what the old Latin name for mercury was, like erganium or something like that, which is where the Hg comes from. Well, we got a mercury atom in the middle, forming a single bond with a chlorine on one side and a single bond with a chlorine on the other side, and no lone pairs. So this molecule would be perfectly straight line. Carbon dioxide is the same. Got a carbon in the center. It's got two bonding pairs shared with one oxygen, two bonding pairs shared with another oxygen, no lone pairs on that central carbon. And so this is a completely straight linear molecule with an angle of 180 degrees between bonds. And I brought little visual aids, which unfortunately the people on Zoom may have trouble seeing. If the Zoom people in the next room want to come in and participate with the visual aids, you're welcome to do so. Unfortunately, I only have two of them. I'll start one up here and one back here. And just take it back. So here's a little model of a linear molecule. This is actually carbon dioxide. It may take a little while for these to work their way around to you, but hopefully you'll all get to see them. Right, so the key thing here is we got three atoms, and they're all in a perfectly straight line. So those two covalent bonds are at an angle of 180 degrees. There's another kind of geometry where the atom in the center has no lone pairs. This is called a planar molecule because the entire molecule lies in a flat plane. Even though there are four atoms, they're all perfectly flat. So we've got an atom in the center here, represented by the letter X, and it's bonded to a Y atom, bonded to a second Y atom, bonded to a third Y atom, and the angles between those three bonds are all perfectly equal, angles of 120 degrees. This is another one that you probably won't find in living things. The only example I could find anywhere was boron trifluoride. I have a model of it. And if you look at it and lay it on a table if you want to, just to confirm that all four atoms are lying in the same plane. It's completely flat. Hence the name plane. Key thing here is that there are three bonding pairs on that central boron atom, but no lone pairs. Now here's the one that you're going to find in every single living thing on Earth, the tetrahedron.
Everything.
Yeah, you're going to find this in every living thing on Earth. There was a Nobel Prize winning chemist, also at Cornell, Hoffman. What the heck was his first name? Roald Hoffman. And he had a famous quote where he said that the tetrahedron is the most important shape in chemistry because it's the basis of life. In a tetrahedral configuration, tetrahedral geometry, you have one atom in the center bonded to four other atoms surrounding it in 3 dimensions. And all of these angles, every single one of these angles is an equal angle of 109.5 degrees. That's a little hard to tell because we're trying to take something that's 3-dimensional and project it into 2 dimensions. So it's hard to tell that some of those angles in the back are 109.5, but they really are. The little dotted line there is indicating that that little y is going off into the distance. This little fatter line is indicating that this other y is coming towards us a little bit. And I have some visual aids that'll make this easier to understand. Not just my little molecules up here, but I have some pictures that show this better in 3D. So what's happening here is that, once again, you've got all bonding pairs on that central atom. So here's the classic example of this tetrahedral geometry, is the methane molecule, CH4. We've got a carbon in the center with a bonding pair for one hydrogen, a bonding pair for second hydrogen, bonding pair for third hydrogen, bonding pair for fourth hydrogen. And importantly, no lone pairs on the central atom. And so that's why all four of these bonds are equal and they are spaced uniformly in three-dimensional space. And here's a better representation of what this looks like. On the left is what we call a ball and stick model of a tetrahedral arrangement. That pink atom in the center would have 0 lone pairs on it, and then it's bonded to 4 other things that are then distributed equally in three-dimensional space with equal angles of 109.5 degrees. And then the little rotating GIF file also shows it. I hand one around. It's a little different representation. These are all what we call space filling models, but it still gives you the idea of what a tetrahedron looks like. Somebody's got my other CO2. I'll collect them all at the end. All right, now, in all the cases I've shown you, in a linear model, a planar model, and a tetrahedral model, we have no lone pairs on that central atom. Things start to get different when the atom at the center actually has 1 or 2 lone pairs on it. And this creates some really interesting geometries that you might not expect. Here's one that's actually pretty common in biological systems, in living things, the pyramidal configuration. So here's how you make a pyramid-shaped molecule. We've got one atom represented by the X that sits at the center, and it's bonded to 3 other atoms, all represented by the letter Y. And the angle between those bonds are all angles of 107.3 degrees. Once again, it's hard to tell that this is happening in three-dimensional space, but there's an angle of 107.3 degrees between 2 of these Y's. And if we took the Y on the right and the Y way in the background, that would also be an angle of 107.3, and same thing between these other Y's. So every one of those 3 angles is identical 107.3. Now, if you're paying close attention, you might notice that that angle is a little bit smaller than the angles in the tetrahedral configuration. In a tetrahedron, you've got 4 angles. They're all 109.5. Here in the pyramid, we got 3 and they're 107.3. They're just a little bit smaller. Now, here's what's going on. Here's why this is happening. Those 2 dots up there represent a lone pair. That's our pair of electrons that were just chilling on the atom in the center. That lone pair of electrons acts as if it was a 4th atom bonded to the central atom. And I mentioned this in a slide earlier, but it may not have made any sense at that time. Lone pairs push harder than bonding pairs. That one lone pair is pushing the others apart farther or harder than they're pushing one another apart. That means that that lone pair is basically squeezing those other 3 bonds just a little bit closer together. That's why their angle is just a little bit smaller. So instead of 109.5, it's 107.3. It's only a difference of 2 degrees, but you know, in chemistry, it's significant. So here's the classic example of a pyramidal molecule. This is NH3 ammonia, which I've shown you a couple times already. So we've got a nitrogen sharing a pair of electrons, a bonding pair with one hydrogen, a second bonding pair with another hydrogen, and a third bonding pair with a third hydrogen. So those bonding pairs are all basically equal to one another. They're all pushing apart with equal strength. But then we've got this one lone pair on that central nitrogen. And number one, that's behaving almost as if it was a fourth atom attached to the nitrogen. And it's pushing harder. So it's pushing those bonding pairs farther away than they're pushing one another. And I don't have a picture to share up on screen, but I do have a model. You can think of this almost like a camera on a tripod. The camera is the nitrogen and the three legs are the hydrogens. So here comes my little pyramidal shaped tripod. The last example of a geometry where you have lone pairs on the central atom is one that everybody learns about in chemistry, and then you might forget it and then have to relearn it again later. This is what's called the bent configuration, and this is the geometry of the water molecule. Now you might think, all right, water, it's pretty simple. H2O, an oxygen attached to two hydrogens. You might just assume that all three atoms are in a perfectly straight line. Right? You might just assume that those two hydrogens are kind of on opposite sides, the oxygen in the middle. But water instead adopts the configuration you see there in the upper right, a bent configuration where the two hydrogens are actually kind of off to one side. And the angle between those two bonds, between the two hydrogens, is 104.5 degrees. Also smaller than the angle that we saw in the tetrahedral arrangement. It's also smaller even than what we saw in ammonia in the pyramidal arrangement. So what's going on in a bent configuration is that we've got one atom in the center represented by the letter X attached to two other atoms, both of which are represented by the letter Y. But the atom in the center, the X, has two lone pairs, not just one, but two lone pairs of electrons. And both of those lone pairs are behaving as if they were other atoms bonded to the central atom. And because they're lone pairs, they're pushing harder than the bonding pairs. So they're actually, especially since there's two of them, two lone pairs, they're squeezing those bonding pairs even closer together, just a little bit. So in a tetrahedron, we had angles of 109.5 degrees. In a pyramidal configuration, we had angles of 107.3. Here in a bent configuration, we only have one angle, but it's down to 104.5 degrees. So it's about 5 degrees less than in a tetrahedron. And so here's our classic water molecule. So we've got oxygen with a bonding pair, with sharing a bonding pair with one hydrogen, sharing a bonding pair with another hydrogen, and then two lone pairs on that central oxygen, which gives the water molecule this configuration you see up here at the top. And, oh, I forgot, I do have a picture of a pyramid. There's ammonia on the left. That's our pyramidal configuration. Yeah, and then our oxygen, or excuse me, our water molecule is going crazy over here. But you can clearly see that bent configuration. As usual, I have models, bent configuration. So if you ever have to draw water in any kind of molecular image, don't put the hydrogens on the ends. Make sure it's got that bent configuration. All right, so summarizing everything we've talked about so far, carbon has a valence of 4. It forms 4 different bonds. And assuming that we're only talking about single bonds, it gets all messy if we start talking about double and triple bonds. But if we're just talking about carbon forming 4 single bonds, those 4 bonds are arranged in a tetrahedron with angles of 109.5 degrees. Nitrogen always forms 3 bonds at the valence of 3. If those 3 bonds are all single bonds, they're arranged in a pyramid shape with angles of 107.3 degrees. Oxygen always forms 2 bonds. And again, if we're talking about just single bonds, those 2 single bonds are going to adopt a bent configuration with an angle of 104.5 degrees between them. And hydrogen only forms 1 bond. So the concept of bond angles is irrelevant with hydrogen because it can't sit at the center of 2 bonds because it only forms 1 bond. And as I mentioned, this is applying only to single bonds. Once you put double and triples in there, it gets a little messier. But why does any of this matter? So, as I said, you know the valence of these common elements that are found in organic molecules. You have an understanding of bond angles and geometry of the kinds of bonds that are formed by these different elements. This is really useful if you ever have to draw a molecule and you need to make sure it's accurate. You want to check the accuracy. Or if you're an art director at some point in your career and you have to check the accuracy of somebody else's artwork, just like putting the spleen on the wrong side of the body or having the subclavian artery go in front of the anterior scalene muscle. Just like an anatomic error, if somebody creates an illustration of a molecule and there's a nitrogen atom with 5 bonds, that's probably wrong. Or a carbon atom that only has 2 bonds, where are the other 2? There should be 4. And similarly, checking the geometry of the bonds. If you see somebody create an illustration and they draw water as a linear molecule with an oxygen in the middle and 2 hydrogens on either end, they're not a trained medical illustrator. But even if you look down here in the bottom right, I know it's a little small, but even when that oxygen is part of a larger molecule, the 2 bonds attached to that oxygen are still going to have that same bent configuration. So here we see something that looks kind of like water. That's actually OH. That's a hydroxyl group attached to a carbon over here. But those 2 bonds have a 104.5 degree angle. That's a bent configuration. There's a nitrogen right there. It's a little hard to tell in this angle, but that nitrogen is sitting in a pyramidal arrangement. And every one of the carbons in there, unless there may be a double bond down here, but most of the carbons are all single bonded to 4 neighbors. Every one of those is a tetrahedron. So that's an accurate model. Now, I had to kind of refresh my memory about all of this stuff way back 30 years ago when I had to start drawing a lot of molecules, because at that time, there really weren't a bunch of databases online where you could go and download 3D models, 3D reference models of molecules. Or if they were in their infancy and I didn't know about them. Nowadays, you want a 3D reference for a molecule, you just go and download it online easy. But back then when I was working for that oncologist and he kept asking me to do illustrations of chemotherapy drugs, he would send me a picture like the one in the bottom left. It's known as a skeleton diagram. Now, the skeleton diagram is a type of shorthand that omits a bunch of information. Number one, it's completely flat. There's no 3D information in that picture at all. All right, I take that back. There's a teeny bit. The little wedge-shaped bonds are coming towards us. The little dotted lines are going away from us, but that's not a lot. There's virtually nothing in there that gives you any kind of 3-dimensional information. The other issue with this kind of picture is it doesn't even show all of the atoms. It's a shorthand way of representing a molecule where you simply leave some atoms to the imagination and you have to know how to fill in the blanks. So there's something up here called R, which usually just that means a variable side chain. All right, there's an O right here at the end of this double bond, so I know that's a double bonded oxygen. But you see that corner point right there, where the R comes down and the O over here, and then there's another line going to that N? That corner point, that's a carbon. You have to know that every corner point and every end point in a drawing like this is a carbon, unless it's specified. All right, there's a nitrogen up here between these two bonds, and that nitrogen is attached to a hydrogen. But then that little wedge-shaped bond comes down, and right there, there's a corner point. 3 bonds coming together. That's another carbon. Come down here to this corner point, where this double bonded oxygen is attached to that little square. That's a carbon. All right, this is a nitrogen. We know what that is. There's another carbon up here at that corner. There's a carbon at this corner point. There's a carbon at this corner point. There's a carbon at this corner point, attached to that S and making up part of this pentagon right here. But then you see these 2 black lines. I follow those out to the end. The end points of lines are also carbons, unless otherwise specified. So that means there's a carbon out at the end of this line and another carbon at the end of that line. So you'd have to know these shorthands. You know that every corner point and every end point of a black line is a carbon in, and then kind of fill that in. What else? In addition to not showing all of the carbons, it also doesn't show all of the hydrogens. It's got 2 of them, but it's missing a whole bunch. So what you have to do is you have to go back and fill in your missing carbons and then count the valence. Look at every single carbon atom in the picture and make sure it has 4 bonds. And if it doesn't have 4 bonds, that means there's a hidden hydrogen attached to it. So we know there's a carbon up here because there's a corner point. It's got 1 bond to the R, 1 bond to the N, 2 bonds to the O. That's 4. That carbon up there is happy. How about this carbon? It's got to be a carbon at this corner point. We got 1 bond to the N, 2 bonds that are part of this square. That's only 3. So that carbon is missing a hydrogen. So there's also a hidden hydrogen at that corner point. Same thing over here. There's only 3 bonds shown. That means there must be a hidden hydrogen. And it's actually, you can see them in here. There's one of the hydrogens in this 3D model. There's the other one kind of off in the distance back there, but those are the missing hydrogens. We're missing one here also. So we got 1 bond, 2 bonds, and then the dotted line, that's a 3rd bond. But there must be another bond there. So there must be a missing hydrogen. And here it is right here in our 3D picture. This carbon is happy. It's got 4. We got 1, 2, 3, 4. But remember I said that the endpoints of lines are also carbons. Well, if the endpoint of this line is a carbon atom, we only see 1 bond, right? The bond that's connecting that carbon to the rest of the molecule. There are 3 whole bonds missing. And sure enough, if you look at the 3D model over here, there's 3 hydrogens attached to the carbon at that endpoint. Same thing with this little stick down here, this little endpoint. There's 3 hydrogens attached to that carbon atom as well. So, so a client could actually give you a little stick figure like this, and you could try searching the online databases to see if you could find a 3D model of it. You might not be able to. It might not exist. It may be that nobody's actually created a model of it. Now, later in this class, I'll show you a nice little cheat that I wish had existed 30 years ago when I started doing this. There are now tools that allow you to draw your own model. You draw the sticks, and it spits out a 3D file. Was
To
it?
do all the like,
Yep, calculates the bond angles. It minimizes the energy, so it finds the most energetically stable configuration. Oh, and I think it fills in the valence, or at least there's an extra command you can run to fill in any missing hydrogens. So here's an example of a molecule that I created in Illustrator just as a simple ball and stick type picture, but based on this stick diagram, the skeleton diagram down at the bottom. So I had to figure out that actually this is not quite the same. It's close. I got a CH3 here and there's an OH in the picture, but otherwise it's identical. So I had to know that, for example, there's a carbon at this corner, there's a carbon at that corner, there's a carbon at that corner, and this carbon only has 2 bonds, so I had to add 2 missing hydrogens to that carbon and add 1 missing hydrogen to this carbon. This one's happy, this one, wait, 1, 2, oh, this one actually shows the hydrogen already on it for some reason. Here's a little more complicated one, vitamin E. But it's this one's not completely 3D the way I would like it, but it's more 3D than this flat thing up here. And more importantly, it fills in all of the hidden atoms. Right. Last concept I want to introduce to you before we run out of time today is that atoms have size. They have a diameter. Now, we can't actually see atoms, remember, because they are much smaller than the wavelength of visible light. So light can't reflect off of them, so we can't ever see them. But there are tools, which we'll talk about later in the semester. There are tools that allow us to determine the 3-dimensional geometry of molecules, the 3-dimensional spatial relationships. And we know roughly what the diameter or radius of each atom is. And there's something called the van der Waals radius, which I put the formal definition at the bottom that I found in a chemistry book. Half the distance between 2 unbonded atoms at which they begin to repel each other. So in other words, you got 2 atoms, their nuclei represented by the black dots. Each atom is basically a cloud of orbiting electrons. As those atoms start to get closer to one another, at a certain distance, they start to repel because the electrons start to repel one another. And so that's basically a way of measuring the diameter or radius of an atom. And this is another concept that we owe to my hero, Linus Pauling. After earning his Nobel Prize for determining, for applying quantum mechanics to understanding the nature of the chemical bond, he also introduced the concept of the van der Waals radius and was the one who measured the van der Waals radii of many atoms. Don't ask me how he did that. How do you measure the diameter of an atom that's way too small to see, but somehow he did. And so now as illustrators, we use this concept because you have to recognize that the hydrogen atom is really small. Oxygen, nitrogen, and carbon are all pretty darn close to one. Some ions are quite large. Sodium is really big. Potassium is even bigger. So what I've done here is I've drawn our super simplified periodic table with a simplified representation of the van der Waals radii of these different atoms, these different elements. So there's our hydrogen atom, which is the smallest. There's helium over on the far right, which is not really any bigger. But then you jump down to the second row and boy, lithium is way bigger than hydrogen, even though all we've done is added 1 additional electron shell. It still makes a big difference and makes the atoms much bigger. And then as you go from left to right across the periodic table, they get a little bit smaller till you get over here to neon on the right. Then you add a third shell and sodium jumps up. It's significantly bigger than lithium. And then they get smaller again as you go from left to right across. So you can probably tell that as you go down the periodic table, atoms get bigger and bigger and bigger because we're adding more electron shells. But here's something that's puzzling. Why is it that the atoms get smaller going from left to right? We're adding more electrons. You'd think if anything, you put more electrons in that outer shell, it's going to just keep getting bigger and bigger and bigger. Why do you suppose the van der Waals radius actually gets smaller as you go across each row from left to right? You got.
I don't know if gravity is the right
You-
word,
you-
but
you're-
because of like they said that they're such a magnet, like denser.
Kinda, you're on the right idea. Not really magnets, but what's the difference between the? You're kind of on the right track too. Between the two of you, put your idea of gravity and charge together. Because of electron what? Shielding? Not familiar with that term, if that's a physics or chemistry term. Right. So you were on the right track. You called it gravity, but right. We've got more electrons orbiting. But remember, as we go left to right across the periodic table, we're also adding more protons to the nucleus. So we've got more positive charge attracting more negative charge. So there's a greater attraction between the electrons in the nucleus. So that's why the radius gets smaller as we go left to right across, adding more electrons, but you're also adding more protons, so creating more of an electrical attraction between them. So so you can actually go online and very easily find this same kind of chart, but with actual numbers, so that you can see just how much bigger is lithium compared to hydrogen. What's the difference in size between carbon, oxygen, nitrogen? As far as I'm concerned, carbon, nitrogen, oxygen are so darn close that when I illustrate them, I draw them all the same size, but I always try to make hydrogen noticeably smaller. And if I have something like magnesium or sodium in there, then, I have to make that considerably larger. So this is actually a student project, and you're going to be doing one of these, student project in Illustrator. This is what's called a space-filling model of a molecule, where each atom is represented by its van der Waals radius. And you don't have to draw this from one of those little stick figures. We're actually going to draw this from an actual reference that's exported from a molecular visualization tool, which makes it a whole lot easier. But still, you want to pay attention to things like the relative diameter of the carbons, which are shown in dark gray, the nitrogens in blue, the oxygens in red, and that yellow thing is probably sulfur, which is significantly larger in diameter than the others. And then all the hydrogens are these light gray or almost white ones. And notice that they're significantly smaller than all the others. This is one from my own work. And again, we've got carbon in dark gray, oxygen in red, nitrogen in blue. They're all basically the same. These three things, if I remember correctly, those are chlorine, either chlorine or fluorine, I forget which. And then a lot of hydrogens that are a good bit smaller. So anyway, that's probably a lot more chemistry than you wanted, but that's about as much basic chemistry as I think you need to know to be a medical illustrator. Next lecture, I'm going to talk about a little bit of organic chemistry, a little bit about naming of organic molecules. And then later in the semester, we'll get into talking more specifically about things like proteins, nucleic acids, carbohydrates, and lipids.